So myself, Dr. Chidambaram, I'm an Inspire faculty from Indian Institute of Science. So I do research on membrane research on last 10 years. So my PhD and my postdoc experience, everything on membrane separation process. Uh, I've been in Israel, Technion Israel Institute of Technology for 4 years, then another 2 years in Ben Gurion University. So there are water research, world leading water research centers over there. I gained a lot of experience. So after finishing my 2 postdoc, then I returned back to India with this DST Inspire faculty. I think if you are PhD students, you might know about this program. So they offer for 5 years. So within this, we have to establish our own lab, then we have to get absorbed in the same institute, or we can go to some other institute. So today, actually I didn't know about this program. So I thought that I can give a technical presentation about my research. So then later I came to know that it's like completely the the fundamentals teaching about the membrane separation process. But somehow I'll try to cover the basics little bit. So first I will give you the brief introduction of the water issues, the water contaminations. I think you might familiar all those things, but still I wanted to highlight some of the things. So then later I will introduce the membrane separation process and the types of membranes. I think I didn't touch about the fabrication, but if you want, I can explain you the simple phase inversion and interfacial polymerization techniques. Then later I'll go and talk about the electro-active membranes. So generally the desalination and the commercial industries, they use typically polymeric membranes. Mostly they use the polysulfone or polyether sulfone or PVDF for membrane distillation, and the top layer will be like polyamide. So they do interfacial polymerization for nanofiltration and reverse osmosis. For ultrafiltration, just they keep it with that support membrane, either with polysulfone or polyether sulfone. So here what we do, so we are converting that polymeric membranes into electrically conductive graphene membranes. So that's what we do research on this membrane separation, and you will see while I'm going how it can be applicable for multiple applications. So I'll give you the brief introduction. If you see the top 10 global challenges in the world, so energy and water, it stays always in the top. If you take the survey, so recently in India, in growing countries in India, China, or even in European countries or United States, most of the peoples somehow they are connected with the energy applications or water treatment, water applications, because there is a demand for water and energy. So if you see in this list, next the food and environment, poverty, it comes next only. So always it stays water and energy. So that's what their researchers are more interested on, water energy nexus. So here I would like to highlight, just look at these images. I think probably we might see everywhere. If you go to the rivers or if you go to the stagnant water lakes, you can see such kind of pollutants. It's a man-made pollutant. People simply they are dumping the plastics. Most of the polymers, it creates the issue. And another serious issue is pharmaceutical waste. Whatever the pharmaceutical drugs pills we are taking, again it goes into the toilet and it mixing into the surface water. These we call it micropollutants. These pharmaceutical compounds or organic contaminants exist in a nanogram level. It's not even in the microgram. It's in a nanogram level, few nanograms. These few nanograms, it negatively affects the human health, because for certain disease we are taking antibiotics, some other drugs. So our body is absorbing, from my understanding, 5 to 10% only. Remaining 90% of the waste, it goes and contaminated the groundwater. Even if you are healthy, still you are taking the antibiotics through the drinking water. If you have perfect reverse osmosis system, still it will remove 99% only. I am talking about only the micropollutants, not on the salts or other contaminants, because these micropollutants is having lot of issues. So recently PFAS, polyfluoroalkyl compounds, these are very carcinogenic and it's very harmful, and most of the United States, they started doing research on these last 2 to 3 years on these compounds. This also exists in nanogram level. These PFAS, actually these PFAS compounds, it releases from the beauty products especially. Nowadays everyone, they use the beauty products. Also the cosmetics, and the nail polish, all the beauty products, it contains these fluorinated compounds. It easily leaches into the surface water, then later it penetrates into the groundwater. So we must remove this kind of micropollutants, and we have to make sure that we are not taking again in the drinking water. So and another side, like the Chennai in Tamil Nadu, in the summer, I don't know about Kerala. Kerala, I think they're getting huge rain, so because it's in the Western Ghats, so you don't have much problem. But in other places, in Tamil Nadu, Andhra Pradesh, and Telangana, and also Rajasthan, in about 6 months, we are having the water scarcity. People, they are just standing like this with the pot. They are fighting for the drinking water. Every year it happens. Even if we are getting enough rain during the rainy season, still we don't have the good water management. We are simply letting the water into the pass into the river or into the sea. And look at this data. So just I have collected from the recent review paper, the global freshwater resource. See that glaciers is having about 68.7%, then and the groundwater is 30.1, and permafrost is 0.8, surface and atmospheric water is just 0.4% of the fresh water. Then in overall 97.5% of the water is salt water. Only we have the fresh water is 2.5. Within that, the surface and atmospheric water is 0.4%. Whatever the huge rain we get, but still it's not enough for the present population. And look at this. This is the estimated simulation work recently published on the review paper in the last year in the Nature Communication. The water scarcity data in 2050. So look at this. Look at the India. The water scarcity, urban population. The India looks. So this is actually expand panel. The dark color is perennial and the all over the year, and the light color is seasonal one. So if you compare with other countries, India and China, it stands in the top. So our Indians has to do more focus on the water research, and we have to do the proper water management. We have to go through the proper water treatment. So you researchers, like I think most of the peoples are in a membrane background or water treatment field. So you have to encourage other people. So you have to make the awareness on this water to stop the water contamination and to save the water. So here you see the global water consumption, how much this especially we are taking the water consumption in India is about 277 billion liters per day, and in China if you compare 219 billion liters per day we are consuming. And another side, the health effects, the fatality. So every year around 8.29 lakhs people are estimated to die from diarrhea. Just you compare this data 8.29 liter with COVID death. So we talk about the COVID. It's a very in this pandemic I think most of the people they suffered. Many of us we lost our close relatives or from the family members, so we suffered a lot, but still it is 5.24 lakhs. But if you compare the diarrhea death, it's 8.29. So how does it diarrhea? It spreads through the water, through the pathogen which was present in the water. So you should understand the importance of these contaminants, the pathogens. This out of these deaths, around 2.97 lakhs are children below 5 years of age. The use of this contaminated water leads to 15% of the patients globally contracting infected during their hospital stay. So if the family members, if they are admitted in hospitalized, so if they are during their stay they are getting affected by using the hospital water like tap water just for mouthwash or face washing, somehow it's contaminated. So this is the situation of India. So let me go to the then what is the solution? Of course you know, so there are many available technologies. So there are certain steps of treatments. Just I want to highlight the membrane separation process. Because these are most successful and feasible technology and energy efficient also if you talk about in the large scale applications. There are many other treatments like adsorption, ion exchange or biological treatments, but still the most effective treatment process are membrane separation process. So there are many types of membrane classification. Like porous membranes and non-porous membrane. In the porous membranes, based on the pore size, we classify into many types, like it starts from microfiltration and ultrafiltration, nanofiltration and reverse osmosis. These are pressure driven membrane processes. And then there are certain processes like concentration driven process, forward osmosis, and vapor pressure or temperature driven process called membrane distillation. There are many membrane separation processes are there. I am not going to going into the fundamental of this membrane process, but I would like to show you how does it happens. So if you are working with the desalination process, membrane separation process, you might know about this process. This is a reverse osmosis. Just look at this animation. So generally, if you are separating your concentrated solution through semi-permeable porous membrane, so what will happen? One side, if you keep low concentrated solution, then the other side you have higher concentration solute. So for example, you can take sodium chloride as an example. So you keep 10,000 ppm of sodium chloride solution in the right hand side and just pure water, distilled water in the left side. So if you separate these two solution through the porous membrane, semi-permeable membrane, what will happen? Anybody can answer this? Oh, why it's not moving? Yes, exactly. I think there is no power, right? Will it happen oftenly? Will it come? Okay. So, in that osmosis process, what will happen? The pure water, the low concentration side, you have the pure water. High concentration side, you have sodium chloride, 10,000 ppm sodium chloride. So, what will happen? It should neutralize the concentration. That is the physical phenomena. So, this pure water will penetrate through the membrane, then it will come towards the higher concentration side. In that case, if osmosis happens, then the whole volume of the water will be higher in the higher concentration side, because it has to neutralize. So, this is the natural phenomena of osmosis. But if you want to do reverse osmosis, there is a osmotic pressure, you have to apply the pressure which is higher than the osmotic pressure. If the osmotic pressure is like a 3 kg, 3 bar, for example, it is not the exact data. So, you have to apply more than 3 bar to pass the pure water from concentrated side to the pure water side. This is how, okay, look at this image. So, this is the one I was explaining. So, here you have the concentrated solution, here you have pure water, in between you have the semi permeable membrane. So, if you apply the pressure here, so which is more than osmotic pressure, then what will happen? The pure water which penetrate through the membrane, then it will collect the opposite side. So, this process is called reverse osmosis, just opposite to the osmosis natural phenomena. So, most of the research what we do, we are developing these membranes and we are modifying it and we are making into low cost membrane, because this membrane is highly expensive. We have to replace once in a 2 to 3 years. So, this membrane itself adds up lot of process cost within this reverse osmosis process. So, for this membrane, I think Professor Anil also he was explained, I hope. So, this is the asymmetric membrane structure. This is the cross section of the image. So, here you have the skin layer, the selective layer, we call it selective layer, and this is the support layer. Here you see the finger like structures. This structure formed when you are doing the phase inversion techniques. So, if you cast your polymers on the glass and put it in the coagulation bath, then slowly your solvent will leach out. So, while leaching out, it will create the pores. These pores will be like the fingers. So, you will have the larger size in the bottom. So, it will be narrowed if you go to the top side. So, all the separation process happens only on the skin active layer. So, this is about 50 to 100 nanometer thickness, and this support layer is about 150 to 200 micron, and depends on the process. Some people they make very thin layer, support layer, and some people they extend it. It's based on the applications. So, this is the okay, all right, I think I should manage with this. So, here I show you the different type of pressure driven membrane processes. The first one, which is a highly porous one, the microfiltration. So, usually microfiltration we use in the first stage as a free filter. because it will remove the large particles. Look at this one, the pore size which is in the micron 10 to the power minus 1 to 10 in this range. It means 0.1 to 10 micron range. This microfiltration pore size will be. Then the next process, ultrafiltration. So this range of the pore size is 0.01 to 0.1 micron. So then if you move to the nanofiltration, then 10 to the power minus 2 to 10 to minus 1. Then if you go to the reverse osmosis, there is no pores. So water will penetrate through diffusion process. Hardly you see the pores in the reverse osmosis filtration. So here I show you the example. What are the solutes or pollutants which can be passed through the membrane and which can be rejected through the membrane. So look at this first example. These particles are algae. These sizes are more than this one, above 10 micron. So this separation process is like based on the size exclusion. So there are certain process like electrostatic interaction and repulsion. There are some other mechanisms, but here in the beginning as a fundamental, you just try to understand this membrane is separated based on the size exclusion, based on the pore size. If your pollutants, if your particles is more than your pore size, then it will get rejected. If it's a smaller than your membrane pores, then it will pass through the membrane, then there is no use of such kind of process. So here you have all the examples, bacteria which can be partially removed by microfiltration, and it can be removed 100% by ultrafiltration and follow-up processes. So then if you take macromolecules which can pass through the microfiltration and it can be rejected by ultrafiltration and other process. So micropollutants, look at this one, I have put this dotted line. So it can be rejected, but partially it can pass through this nanofiltration, and it can, some of the micropollutants can be rejected 100%, but some it can pass through even reverse osmosis process. This is what I was explaining in the beginning. Even if you do the reverse osmosis, some of the micropollutants it won't get rejected. Okay, so so what I was saying so far, the membrane separation process is a feasible and successful technologies in water treatment, but there are certain challenges within this process. So what are those challenges and how should we overcome on this one? So if you talk about pressure driven process, let's say reverse osmosis, so you have fouling. It can be classified into organic and inorganic. Inorganic may be called in terms of scaling and biofouling, and another issues which I was speaking just before, micropollutant passage. So in this one, most of my research which focuses on this highlighted one, biofouling and micropollutant passage, because biofouling is very serious issue. I think Professor Anil, he was talking about virus separation and virus fouling. So here mostly I talk about biofouling, the bacteria accumulation on the membrane surface, how it can grow, how can it controlled during the membrane separation process. So what are the technologies available on this biofouling control? So here look at this. This is the membrane spiral wound module. I think most of the people you might know this is the pristine membrane. This spiral wound membranes, it's made up of along with the feed spacer. Feed spacer which enhances that mass transport and the proper mixing of the feed water. And here see the dirty color which indicates the fouling. It can be either biofouling or organic fouling or even scaling, the salt deposit. So once it's get fouled, what will happen? So we talked about many pores, right? It can be blacked. Once it's black, the outcome, which means the permeability, the water permeance, so it can be dropped out. Let's say, for example, if you are getting with your membrane 10 liter per hour for 1 meter square, if you are 10 LMH, if you are getting, then once it's get fouled, in the first day it will get 50 percentage. So 10 liter will become 5 liter. Then the next day, if it gets another 50 percentage, then you will get only 2.5 liter per hour. So then what do you need actually? You need to apply higher pressure. If you are applying 10 bar, then it needs 20 bar. Then it costs double times. So overall your process cost it keep on increasing. So we have to minimize, or we have to prevent in the initial stage of the fouling which starts to occur. At this stage we have to do. There are certain typical process what mostly people are doing in the industry. After running 1 week or something, then they do back washing. So if you are applying the pressure to getting the water, just they will reverse the pressure side. So what will happen? What are the accumulants, foulants which deposits on the membrane surface active layer? Then they pass the pressure from back side. So it can remove, but it is irreversible. You will not get 100% removal during this process. Then what people, the typical industry people, they do chemical cleaning. Mostly they use dilute acids or dilute bases like sodium hydroxide or hypochlorite. These are the chemicals they use. They use the dilute acids and hypochlorite. What will happen? It will damage the active layer, that separation layer, which I shown in that same image, that is about 20 to 50 nanometer. So easily it can negatively affect that membrane surface, that active layer. Then your rejection performance will get lower. So for this process we need the alternative technologies. So that's where we focus. So for that process we started to do the research on electroconductive membranes. Initially I was working with carbon nanotube membranes. I think you might know about CNTs. So there are single-walled, multi-walled carbon nanotubes. So we started with multi-walled carbon nanotubes and we made it self-support membranes. Mostly if you read it in the articles, what they do, they commercially buy or synthesize the nanoparticles. Just they mix it about 2 to 5% of the CNTs in the polymer. Then they will make it as a composite membrane, and they will say like PES CNT membrane. It's conductive membrane. But our research started with self-support CNT membranes. Without any polymers, we started to make freestanding the fabrics. So we characterized and we applied this membrane for multiple applications. Especially we focused on biofouling control by applying the electric potential. Since it's a freestanding, there is no polymer, it's highly conductive. Then if you apply the low voltage, let's say less than 1.5 volt, then it can generate the biocides like hydroxy radicals or hydrogen peroxide or superoxide. Then it can kill the microbes. CNT itself, it has that intrinsic anti-biofouling or antibacterial properties. So it will absorb the electrons from microbes. Then it can damage the cell wall of the bacteria or virus. This is how that antibacterial properties the reported in the articles. In our case, so it works actually, which is 100% true. All the CNTs having antibacterial properties, but if you come to the real process like a filtration process, it won't be sufficient to prevent the bacterial attachment. Like if you do the small scale in a petri dish test, if you keep a small coupon of your membranes and put only few bacteria, then you will see the antibacterial properties. It can kill or it can create that incubation zone, that small zone. But if you go to the real process, filtration process, there is a permeate drag force. So we are applying pressure. So all the bacteria which move towards the pressure towards the membrane surface. So that intrinsic antibacterial activity was not effective for this reverse osmosis or ultrafiltration or nanofiltration process. So what we did, we applied the electric potential as said, then we make it as electro-active membranes. This is the key points of this technology. We have filed many patents on this work. Then we started with, we stopped this research and we started with graphene membranes. You know, graphene is same family, carbon family, but it has high thermal and physical properties. So it can be applicable for many applications, including supercapacitors, batteries, fuel cells, and also for water applications. But the fabrication process, it's a very lengthy one. You cannot prepare the graphene within a day or within an hour. So it takes longer time. So then for characterizing it, then it should undergo for another 1 or 2 weeks. So for this purpose, our collaborator from Rice University in Texas, so he actually first invented this material called graphene. They call it laser induced graphene because it was fabricated under laser. Just they have taken the polymeric substrate, then expose it under the 10.6 micron CO2 laser. Laser, you know, right? So it creates lot of temperature, but in a few seconds it creates high temperature more than 1200 degrees Celsius. So then it can convert the polymeric materials into graphene within a second, even in a millisecond. So it can convert the polymeric materials into graphene. It's about 40 to 50 micron thickness. So you will have your base membrane. For example, if you take your custom made ultrafiltration membrane. So this is polyether sulfone membranes. So here we made the circular pattern. So this white part is just the support polyether sulfone membrane, and here we made it this laser induced graphene. This is a highly conductive and stable. So easily we can apply the electric potential for biofouling prevention. So later our collaborators, they started to work on with different materials for application. Also they tried with food, wood and cloth and cardboard. So they later come to the conclusion that at any carbon precursor they can convert into graphene. Most of the polymers can be converted into graphene. But there is a disadvantage for the membrane process. I will tell you the later, because what will happen if you take your ultrafiltration membrane, it can convert that selective layer. So then you will have more pores. It will open up the pores. Then you will lose the selectivity. But this membrane behaves as different functional membranes. I will tell you. So there are lot of advantages, also disadvantages. I will tell you how to overcome all these things. And like if we highlight this is a low cost fabrication. Within 5 minutes I can make like 10 by 10 centimeters graphene. I can make it, and it can be like a fast and scalable process. Even if you want to go for spiral wound, because spiral wound you need a larger surface area, I don't know how many of you working with spiral wound. Most of the people you use the flat sheet, the small cell, right, or stirred cell. So, but if the real application works if you demonstrate your research in a spiral wound membrane. You are a chemical engineer, I think most of the people. So, it won't be exactly same. If you do the small scale and if you replicate, it won't be exactly same. So, there will be some difference. So, you have to optimize for each size. Yes. 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 Yeah. Yeah, I'll tell you. So, what happens, this is kind of a photothermal process. If you talk about the graphene synthesis, so there is a CVD and a plasma technology. Some other, like recently they started with reduced graphene oxide using different oxidizing agents. So, everything involves the photothermal process from my understanding. I am not a carbon chemist, but still. So, what happens in especially on this process what we studied. So, once it hits the polymeric substrate in a millisecond, all other elements like whatever nitrogen or phosphorus or oxygen, whichever is attached on the polymeric backbone, it can release immediately. Only the carbon it can relocate and formed as a graphene. It was like it was not a planned research. So, our collaborator, he was trying to hit the laser on graphene oxide for some other purpose. That graphene oxide was coated on the polymeric substrate, polyimide, that the first figure. By mistake, the target was hitted on the polyimide instead of graphene oxide. Then he noticed that there was a graphene material, there was a black material. Then immediately he asked his students to analyze it, because the best tool to analyze and confirm the graphene is Raman spectroscopy. So, if they see whether it's that the defective peak is dominant or not, based on that they can calculate that IgD ratio. So, then they confirm that this is a graphene. From that point they were so much interested on this because of the easy process, and they started on this research. They worked on the energy application. Our team in the Ben Gurion University in Israel, we started for water research. So, this is how we started. We confirmed with Raman spectroscopy. So, there was no other, this is a completely pure photothermal process mechanism. And after we started this research, many research group, they tried with different lasers. We started with CO2, 10.6 micron CO2 laser. Other peoples, they tried with 1025 nanometer also, they tried with 675, many lasers they tried. So, based on the laser power and the speed of the laser, so we can tune the surface properties. We can make it into super hydrophilic to super hydrophobic. So, it can be tunable process. And another advantage of this process is we can do any kind of pattern on it. Pattern, which means drawing. Even if you give me your photograph, I can load into the software, then we can make a graphene exactly on your photos. Because of this easy application, it can be applicable for sensing application especially. We started, one of my students, he started the research on micropollutant sensing. For sensing, this is electrochemical sensing what I am talking. So, we need different kind of electrode strips. So, we need different kind of patterns on it. So, for this purpose, for example, if you go for CVD synthesis, you cannot make such kind of pattern on it. Here you can design. For example, this also, look at this owl structure. Just imported from other source and printed on the cloth. So, any kind of pattern you can make it on this one. So here I show you if it works. I'll show you the short video. The base membrane, and the base is the membrane which was the custom made polyether sulfone, so ultrafiltration membrane. Here we made it the rectangular shape pattern, so because of the size of the cell which we have to analyze it. So this is how the laser will go to and fro, then immediately it can convert the polymeric materials into graphene. I think it stopped. There was some issues with that connection. We struggled for 5 to 10 minutes. So now it seems okay. So since I talked about the biofouling control, I would like to highlight how does it happens. So look at this beautiful image. One of my colleague, he made this one and published in a review article. Look at this time scale, second, minute, few hours and hours to day. So this is the schematic of the membrane surface. In a few seconds, the contamination, that the pathogen which was present in the wastewater, it can touch on the membrane surface. Then most of the bacteria or virus, it can be like reversible. So it can go off. Only few cells which can attach on the membrane surface in a minute. Only few cells. You can talk about because if we talk about the bacteria, mostly we talk about 10 to the power 2 or 10 to the power. In the tap water, generally, if you analyze it, the population will be 10 to the power 2 CFU per ml. So here, in a minute, there will be a few bacteria which attaches. Then in a few hours, it can form a few colonies along with some amount of extracellular polymeric substance, EPS. So this EPS will help to grow further biofilm. Then in hours to days, it can form as a thick biofilm. So just one day or half day is enough to grow a thick biofilm. Even a single colony is attached on the surface. So our research mostly focused on controlling the biofouling or preventing the biofouling in the initial stage of attachment. Because once it's get fouled, it is very difficult to clean the membrane surface. Even if you do with chemical cleaning, as I said, it can negatively affect the selective layer of the membrane. It's very difficult. So here I show you some of my research examples. We have studied especially for this biofouling prevention experiments. So we have run for 3 days using model bacteria. So by supplying the nutrients, the carbon source, we have taken LB and continuously we supplied, we have given the food to the bacterial growth. We estimated this bacteria like it can grow within 72 hours, which is mimicking about 6 months to 8 months of the real experiments. So that's what we calculated. So accordingly, we have mixed the bacterial culture, then we keep on passing the nutrients. So we have separately studied one control experiment, then one electroactive membrane. So in this electroactive membrane, we have applied certain voltages. So we make it electrically active. Then you see there is only few colonies which was attached in this right side membrane. So we call it the graphene membrane, laser induced graphene at 1.5 voltage electricity. This was demonstrated under filtration, because if you are testing just with the cross flow, there is no presence of this permeate drag force, but if you are demonstrating the experiments under filtration, there is a dominant of permeate drag force. So, which will push all the bacteria or microbes towards the membrane surface, then forcefully it will be attached, then it can develop the biofilm. So, at this condition we studied with 1.5 volt, we demonstrated and successfully it controlled and prevented the biofilm formation in this membrane. So, this one we studied with just polyether sulfone ultrafiltration membrane. And then we wanted to make as a strong intrinsic antibacterial properties of this LIG membrane. As I explained earlier, so graphene and CNT is having antibacterial properties, but which is not much effective under filtration mode or membrane separation process. It is having, but it is not much effective. So, for that purpose we have added silver salts into the polymeric membranes. While preparing it, we mixed certain amount of silver salts into the polyether sulfone membrane, then we made it as a composite like a silver nitrate doped polyether sulfone membrane. Then we exposed under laser induced graphene. Then what happened, it converted this polymeric membranes into graphene. Along with it also generated its synthesized silver nanoparticles, silver 0 nanoparticles. So, it is a very easy simple steps to create like silver doped membranes. Then we demonstrated, we characterized, I think you might know, all PhD students, what are the characterization we go for, like since it is a carbon material graphene, we do especially the Raman, and we go for XPS and SEM. We confirmed that this is a silver doped laser induced graphene. Then we demonstrated this again for the biofouling experiments. Again the condition is similar to the previous example, it is a 72-hour experiment. So, we supplied the carbon source continuously, we applied the electricity. In this case, sorry, we did not apply the electricity because we wanted to make it intrinsic antibacterial membranes. So, in this one control, you have see the fluorescence intensity. These all are confocal scanning microscope images. So, after we complete the experiment, we have to do the dead life staining. So, it is kind of dyes. So, your bacterial RNA, DNA, it will absorb the dyes, then it will be reflect under the microscope, the confocal microscope. This green color which indicates the live cells and biofilms, this red it indicates the dead cells. So, here you see the control PES membrane, and here the PES membrane doped with LIG. Even without electricity, in absence of silver, this is effective, but still we wanted to avoid, because after few days, if there is a few colonies or in a few spots, then after certain days again it will develop the biofilms later. So, that is what we wanted to avoid, even this kind of spots. In this one, the third case, just silver doped PES, silver nitrate doped PES. Since there is a silver, so it killed most of the bacteria, but still attachments are there. If there is attachment, of course, ultimately your flux, your water permeability will drop. So, in this case, in the last case, silver dope with LIG, we eliminated most of the bacteria, only you see the few spots and all of them are in dead state, inactive state. So, this is how we made it as a intrinsic antibacterial properties of our membranes. And then what we did, so as I said, since we are damaging or open up the selective layer of the membranes when we are doing this laser induced graphene, so we wanted to make it highly selective. In that purpose, we tried with, we have infiltrated graphene oxide, the synthesized graphene oxide nanoparticles, under vacuum. Then we did the cross linking with glutaraldehyde, and then we made it as a highly selective membrane. So, which was comparable with the existing polymeric ultrafiltration membrane. So, we demonstrated this one for the same anti-biofouling, and here we notice that about 10 to 15% of the flux drop was decreased in this case. Then what we have done, instead of modifying the membranes, because in the general aspect, if you do the modification on membrane surface selective layer, so ultimately your flux will be dropped. So, there should be a trade off between the permeability and selectivity. To avoid this one, so what we have done, instead of touching the membrane surface, we have taken the existing membranes, the RO membranes or nanofiltration membranes. So, we wanted to make it antibacterial feed spacer. Look at this image. This is a very nice image I have taken from the Google. So, this is the spacer grids. I think you might see, if you open the spiral wound membranes, you can see that spacer, feed spacer layer. You see this all yellowish color, that colloidal things is mostly because of the biofilms. And wherever this joints which touches on the membrane surface, so there is a more chances of biofouling on the membranes, because here there is a gap, here there is a less chances. Wherever these joints, the grid joints are there which touches on the membrane surface, which can develop the biofilm. So, that is what we wanted to make it as a antibacterial spaces. For that, so we have used, first initially we started with the prototype spacer. So, using the polyimide substrate, we just draw the pattern, and we made a spacer. This is a prototype, and we demonstrated this is we studied this spacer along with the RO membranes, the commercial RO membranes, and we noticed that it's the thick biofilm. Look at this same images, and the control, here we see some of the bacterial spots, but is still significantly low contamination or low biofilms. So, this was the interesting studies. Then we got the project from the ministry, and they wanted to make actually convert the commercial feed spacer into graphene. So, that was the scope of the project, but unfortunately that polypropylene, this was completely melting when we exposed with the laser. So, we tried with different parameters. So, we controlled the power and speed of the laser, but we could not able to do it. Then somehow we wanted to finish this project. Then what we have done, we have scrapped the laser induced graphene powder from the membranes or the polyimide. So, we collected the graphene nanoparticles, then we mixed it with the glue. This is a kind of special glue. So, we went for the patent on this one. I do not want to say the glue name here. So, we just mixed it with the glue and we made it as a conductive glue. Then we simply did the deep coating on the existing polymeric spacer, polypropylene spacer. Then we made it as a electrically conductive. Then we adapted this spacer into the spiral wound module and demonstrated that, which was working very well. Recently this paper came out in the advanced material and interface. Then as I said in the beginning, our research mainly focused on biofouling prevention and micropollutant removal. So, since it is electrically conductive, during our experiment and research, we noticed that so there is a generation of biocides and so hydrogen peroxide. So, we wanted to apply our membranes for organic pollutants removal also for inorganic thing. So, we have taken one inorganic heavy metals, hexavalent and chromium, and one pharmaceutical compounds. So, we studied together under the separation, the filtration process. We applied the electricity here. So, here mostly what we done, so we have applied the cathodic potential on our membranes, because our setup was like inbuilt stainless steel electrodes. So, we used our stainless steel parallel electrode as an anode, then we applied the negative potential to the LIG membrane. So, then it acts as like so just so the one will be like a cathodic. So, here there is a reduction reaction happens. So, what happened that chromium 6 hexavalent chromium, it reduced into chromium 3. I think most of you know it's like hexavalent chromium is more toxic. So, then we brought into less toxic trivalent chromium. Similarly, we have taken this ioxol, this is iodinated contrast media. So, here there is many, I think 3 iodine groups in this structure. So, we have like removed all the iodine, it is like completely the de-iodination happens with this membranes. This also we have published in ACS Applied Materials and Interface. And currently what I am doing, so we are doing the membrane distillation process. Since we can tune the surface property, surface energy, we can make it into super hydrophobic. So, I wanted to try with this membrane distillation application. I think Dr. Noel is also doing, and many of the other peoples are doing the membrane distillation. So, this is the typical setup. If you pass the hot water and cold water which was separated with the super hydrophobic membrane, then there is a vapor pressure difference. So, then with this super hydrophobic membranes, only vapor which can penetrate through it, then the other side it can condensed. So, this is the typical the phenomena. I think in the next slide I will show you. So, what we have done instead of PVDF membrane, so because PVDF is hydrophobic, and in some cases they do some kind of polymerization and make it to super hydrophobic, or they are doing some kind of silane coating and make it into super hydrophobic, then they study for this membrane distillation. My intention is, because this is it consumes lot of energy, because we have to heat it up. The feed water should be in the range of 50 to 60 degrees Celsius. So, we have to heat up the feed water. So, it consumes lot of energy. If you compare it with reverse osmosis and nanofiltration, this is highly energy process, so expensive process. So, that is what. So, just I am inspired with this natural desalination process, many people are of course doing. So, since our graphene is a photothermal materials, so it can harvest the solar energy. So, look at this natural phenomena. What happens? This sea water, it gets heat up with the solar energy. Then there is a evaporation process. Then it condensed the cloud. Then we get the pure rain. The similar process, because here if you want to heat it up and you want to evaporate it, you need lot of sun, lot of energy. So, then only you can create the vapors. So, for that purpose our membrane is useful here. This is the our experimental setup. This is a very small setup. We have inbuilt the quartz glass to absorb and transfer the solar energy. So, here we used the halogen bulbs. We used 50 watts, 4 numbers. Then the temperature, the feed temperature here it didn't rise up. So, what happens? Only the interfacial layer of the membrane, only the membrane surface which gets heat up, then there is a vapor formation just which very close to the membrane surface. We are not heating up the whole feed solution, just which was close near to the interfacial layer of the membrane. So, but the flux rate was very low, but it can comparable with the other solar driven process. We get around 1.2 to 1.5 liter per LMH. Then we characterize these membranes and we confirm this graphene with Raman, and look at this structure. This is a highly porous, but still it works, and the contact angle is about 145 plus. And we check the performance of this membrane distillation membrane and this laser induced graphene membrane. We almost get 99 plus percentage of the rejection for sodium chloride and sodium sulfate and the kind of textile dyes, also for one of the pharmaceutical compounds. So, also we studied the heavy metal ions arsenic, cadmium, lead and chromium. So, we get almost 100% of the removal. So, it is actually I can say it is a successful process, but still the permeability is very low. So, it takes longer time with the, but it can be comparable, as I said, with if we compare it with other solar driven membrane distillation process. So, it can be comparable. Still, because I do not have the energy background, so still I am trying to collaborate with some other peoples to enhance the performance in terms of permeability. Though so far the rejection looks very good, and still we did not publish anything on this one. Still we keep on working on this one. Also I checked the long term performance. So, at this 1.2 to 1.5 liter per hour, so it works up to 100 hours, 3 to 4 days it works, but still we wanted to demonstrate this one for longer run in a week or a month. So, then only we can know our membrane is capable of doing this solar driven membrane distillation or not, because ultimately we wanted to go and make it as a prototype module. So, because in India we get lot of sun, right? So, it can be easily we can make a prototype and we can give this technology to the rural peoples, because here somehow we can get 99% plus of the removal of all the pollutants. In addition, in this work we have checked the biofouling formation also. In the membrane distillation, most of the peoples they do not talk about biofouling, but still there is a problem. So, for this purpose again we applied the electricity, especially for biofouling experiment, and then we observe the similar trend what we have got with the previous works with the pressure driven membranes. So, we got the similar one. So, here we used both LIG as anode and cathode. In the both cases we see almost complete removal of complete prevention of biofouling or biofilm formation. I think yeah, that is it. So, these electroactive membranes, you can see it can show multiple applications, not only in the water treatment. As I mentioned in the introduction, it can be applicable for energy applications like supercapacitors, batteries, fuel cells. So, it can be applicable for various applications, since the key features of the easy fabrication and scalable. And these electroactive membranes have more advantage than the polymeric membranes, because so we can do in situ cleaning or in situ oxidation reduction of pollutants. So, these are the advantages of these membranes. And this super hydrophobic membrane, of course, it can be applicable for solar driven membrane distillation process. So, this has the potential for producing water sustainably, because we have the technology already existing everywhere. So, we want to minimize the energy consumption. That is what the present water researcher or membrane researchers they focus on it. So, our research also stays in the same line. So by that I finish my talk, and I would like to thank our Department of Science and Technology, and of course our institute, Indian Institute of Science, and our host Professor Praveen, and our collaborator Dr. Christopher Arnosh, and my students Yashpal, Siddharth, Amruta, and Akhil. And thank you very much. So if you have any questions, if you understand, so you can ask me. I'm very happy and glad to clarify that. Yes.
Question might be basic.
Yeah, sure.
Thing is, I've seen laser-induced graphics of polyamides
Okay.
energy applications.
Mm-hmm.
I've seen,
Okay.
but my doubt is this will be what laser-induced graphics will brittle, right? Little bit brittle compared to a polymer film.
Yeah, compared to polymer film, yes, you are right.
So when you convert a flat sheet
Mhm.
into a spiral bound,
Yeah,
the brittleness might cause a defect in the this thing, right?
you are right.
So that might so I'm asking that would that be a major issue in this, like when you
Yes, you are right. That is a major issue. Actually, that's what we tried with PVA coating. So in one of the article, so what we have done, exactly the same thing we were thinking about to make it as a spiral wound. Even with the flat sheet, with the long run, we can see some of the leaching out of these nanoparticles, graphene nanoparticles. So we wanted to avoid it, but still we want to keep the same electrical conductivity, because that is the key point for our applications. So that's what we have done the PVA coating. If I remember exactly, so we have taken 0.2% PVA. So then the conductivity is decreased about 30 percentage, but still we have demonstrated that biofouling prevention. So it shows the similar trend. So it works very well. So if someone wants to upgrade it for the spiral wound, because the spacer we have upgraded using that dip coating technology, but the membrane we didn't go for it. But it is a possible, I can say last few years only people they started on this research, because once started the research, it will take a decade to make it as a prototype or commercialize it. But from my perspective, this electroconductive membrane has a lot of potential. So everywhere challenges are there. So we have to overcome, and many people's they should get the interest on these topics. They have to develop it. Then ultimately, so it can give the good fruit. Yes, then? Yeah. Sorry? Yeah, I tried with DCMD, then later I switched to vacuum. Yeah, VCMD. Maximum? In our case, we checked with IR thermometer. Our membrane gets about 80 to 85 degrees Celsius. With this, I think we used 200 watt. But if you use solar simulator with one sun, which is 1000 watt, right? Yeah, 1000 watt. I think in that case, you will get maybe you will get higher permeability. Right now I don't have the facility for that because it's expensive. We need to but this one, the concept is working, so I have to lift it up for the next step. Yes.
Biofouling is prevented when when it's connected to
Electricity.
some voltage.
Yeah.
Some voltage is something. So that means during a run that is not possible. During a filtration run that is not possible. Right?
You mean to apply the electricity?
Yeah.
No, we are continuously we are applying the electricity during the run.
So then when it is scaled up, then that the potential that has to be applied will be much more.
Much more. That's what we demonstrated with this spacer with the small coupon. We applied 4 to 5 volt. When switched to spiral wound, we applied 12 volt. So
As the size of
yes,
the
exactly.
increases, then
Yes,
but it's continuous.
it's a continuous.
Why not intermittent? I mean, I'm just asking. Like, if it
We tried actually not with this LIG. We tried with CNT, but the performance was not good. So what happens? as I explained in that biofouling formation, it gets formed already. So, if you stop it, then already it started to accumulate it, then it is not like
But
detaching.
if you have silver, like for example,
Mhm.
if you have glass vessel, if you
Yes,
have
yes.
silver, so that would even passively it can kill, right?
Yeah.
Then you might make it intermittent also. That could also.
Yeah, that could be possible, but the thing is, the nanoparticle dopants, I'm not much happy about that, because
leaches out.
yeah, it leaches out, and also after certain time the effectiveness is not there. Slowly it's decreasing. So that's what we wanted to make it active always. Uh, okay, and yes,
I don't know, but I'll try. Can give a pulsating volt
Mhm.
that might
Yeah,
reduce the continuous.
continuous, yes, yes.
Pulsating can be
Yeah, that's what Dr. Noel asked. So we tried, actually we tried with alternative current as well. We changed and we played with the different frequency, because if you increase the frequency, that the pulse rate, the switching plus and minus, it will increase. So that was better if we apply in the continuous mode, but if we do the pulsing like in between, in a few hours gap,
few hours. Like I'm telling you, pulsating continuously.
continuously. Oh, okay. So that's
One pulse.
yeah, that's we have tried. So that was better actually compared to the DC power. So that was better. If I understand correctly, that is alternative current. So that works very well. All right. So no more questions. Okay. Thank you for listening, and hopefully some of you will get interest on this electroconductive membranes. So of course you can contact me. I'm very happy to help you if you want to visit me, or if you want to collaborate with me, I'm fine. So you can take this approach to your PIs. Okay, great.